When we talk about gases, we know that there are 4 measurable qualities of a gas: volume, temperature, number of molecules, and pressure. So we will have this equation PV equals nRT, where R is a constant, and we will actually go through this a little bit later, but we will cover a lot of gas laws that deal with all of these values and variables. So pressure, when we talk about gases, we have to talk about pressure, and pressure is force per unit area, and so force is measured in newtons, and force is caused by gas molecules hitting a wall, and their collisions is what the pressure is measuring. So the air around us exerts a pressure on us. So if we would go into outer space, because the air around us is exerting a pressure on us, what would happen if we went into outer space? Well, our eyeballs would explode because there is no pressure pushing onto our bodies. We just don't feel it because there's equal pressure from our bodies pushing back. So the most atmospheric pressure would be at sea level, in the ocean bottom, and then at sea level, and then in the mountaintop. Because the ocean bottom would have the atmospheric pressure as well as the water pressure pushing down on it. So measuring atmospheric pressure, we generally use a barometer. So a barometer just looks at the pressure pushing down from the air, and this is a vacuum here. So the more the pressure that's pushing down here will push up the mercury. It used to be mercury in here, and it will push up the liquid in the barometer, and we can read it with millimeters of mercury, so the pressure in mercury. So that's why it's in mercury, is that's how it used to be measured. So the lower the elevation, the higher the pressure from the atmosphere. If you see right here, the atmosphere at sea level is 760 millimeters of mercury, but the atmosphere at elevation is 714 millimeters of mercury. So atmospheric pressure does vary based on sea level. So again, a barometer, just note the air pushing down here. With the vacuum on the inside, nothing is pushing down the liquid on the inside, so the more air pressure would actually make H, the value of H, increase, because if there's more air pressure pushing down, it would mean that the liquid would be forced up the tube a little bit more. So that's basically how a barometer works. A manometer is a way to measure an unknown gas pressure inside of a container. So that's really important. It's a way to measure an unknown gas pressure inside a container. So here, if the gas pressure is less than the container, we know that it's the pressure of the atmosphere minus the height of H. If it's more, it's the pressure of the atmosphere plus the height of H. So here's how you decide whether or not you subtract or add. So if you look at the atmospheric pressure pushing down on the liquid within the container, okay? If it looks like the atmospheric pressure is pushing the liquid towards the pressure inside the container, you know that the pressure on the outside is greater than the pressure on the inside. Thus, you're going to subtract. If you can see here that it looks like the gas inside the container is pressing out onto the atmospheric pressure, you know that the gas inside the container is greater than that on the outside, so that's when you add the height of H. We will review this more when we talk about partial pressure, but basically it's just an addition or subtraction, and you've just got to decide whether or not the inside of the container is greater than or less than the outside of the container. And it actually can be equal to the atmospheric pressure if your values of the liquid line up equally as well. So that's another way to read it. And then just a reminder, STP, we just have that standard to compare things to. So STP is 1 atmosphere and 0 degrees Celsius at sea level, and our pressure can be measured in 1 atmosphere or 760 millimeters of mercury or 760 torr.